earlier videos, we talked about torque as being a twist. That's all it is. It's simply a twist. A force is a push or a pull. A torque is a twist. Like forces, torques are vectors. They have magnitude and direction. We also talked about the difference between a force diagram, which applies when we're using a particle model to describe the physical phenomena, and a free body diagram, which is what we use when we're discussing objects that are rigid bodies that might involve rotation. We then solved a problem by applying the conditions of equilibrium. And as we learned in the particle model, one condition for equilibrium is that all the forces must add up to 0. Now, with rigid bodies, we have to impose another condition of equilibrium, that all of the torques also add up to be 0. Okay, so we then solved the problem with the tipping block, and we applied both conditions. Then we asked ourselves the question, well, this might get a little more complex when we have forces that are directed at an angle, where the distance or the position vector from the origin or from the pivot point right here, that position vector, the line of action, that position vector would be at an angle to the right here. This line of action, position vector, is at an angle to the force. Okay, and we'll call that angle the angle theta. Okay, so the angle theta would be this angle right here, the angle between the force and the line of action of the position vector r and the force F. Okay. One way of handling this is to break down the force into two components. A component that's perpendicular, to the line of action of the position vector, and a component that's parallel. Okay, and so if we break down the force into those two components, we can see that the parallel component right here, the parallel component acts directly through the pivot point. Okay, so it cannot exert a torque about the pivot point. All it can do basically is pull the wrench right off the nut. So we better secure that a little bit. We use an open-ended wrench, or not an open-ended wrench, we use a box-ended wrench, so that when we pull on it, it's not going to come off the nut. Okay. The perpendicular component can exert a torque about the nut. As we pull on this component acts across the moment arm R, it is actually causing the wrench to twist. And so we can express the torque applied to the nut right here is equal to that perpendicular component times the magnitude of the position vector R. Okay. We can further express the perpendicular component as being equal to the force times the sine of the angle theta. Okay. And that should be familiar to us by now. Okay. And so now we can actually calculate the torque, assuming that we know the force and the angle. And we do that, we can then calculate the torque, which would be the force times the sine of theta, which is the same as the perpendicular component, times the magnitude of the position vector r. Okay, so we have a way of calculating torque now. This is an interesting way of looking at it, but it's not the only way. We could also calculate torque in a different way. Okay, so we could write it this way. We could say it's the force times the sine of the angle times the length of the position vector from the pivot point to the point of contact of the force. Okay, and that's a nice way of writing it. Or we could also look at it this way. We could take the r and put it inside the parentheses here. We put the r here. And so now we're saying that, well, an ounce of force equal to, now the torque is equal to the force times r sine theta. Okay? And we have to say, well, what is the significance of that? What is r sine theta? What could that possibly be physically? Okay, and so we'll take a look at that, and we can now express the torque is equal to the force times r sine theta. And if we look at our wrench and the line of action of the force, the line of action of the position vector, we'll extend both of those a little bit, and we'll see that, okay, wow, if I can find the perpendicular distance from the pivot point to the line of action of the force, and that perpendicular distance then is going to be, well, if this is theta right here, if this is theta, this has to be theta. So the hypotenuse is r, and so we can write then that the moment arm is equal to r times the sine of theta, because this moment arm here is perpendicular and it's opposite the angle theta. Okay, and so now we can say, well, okay, let's call that r perpendicular, and we can call that a moment arm. Okay, and it's the perpendicular distance between the pivot point right here. Oopsie, between the pivot point and the line of action of our force. I can take that force here, so I can't get the line. Anyways, it's perpendicular. It's between here's the line of action of force. It acts along this line right here. Okay, it's applied at that point on the wrench, but we can say that this is the line of action of our force, and this is the perpendicular. Oops, this is the. Put that back. This is a perpendicular distance. That's perpendicular. That's the angle theta, and so this r perpendicular is this perpendicular distance from the pivot point to the line of action of the force. Okay. And so now we can express our torque as being equal to the magnitude of the force times the moment arm, or times the perpendicular distance from the pivot point right here to the line of action of the force. Okay. And so that's another way of expressing the torque. So we have two ways. We can say the torque is equal to the perpendicular component times the magnitude of the length of the moment arm, or we can say it's equal to the force itself, the magnitude of the force, times the perpendicular distance from the line of action, from the pivot point to the line of action of the force. So both methods are equally valid, and as you can see, they amount to being the same thing mathematically, but sometimes it's easier to visualize a problem in terms of one way of looking at it. Maybe the perpendicular component is easier to deal with. With other problems, it might be easier just to look at the moment arm. What is the perpendicular distance to the line of action of force? And then calculate your torque that way. Okay. Now these are more common sense ways of approaching a problem. They're not highly mathematical. They just involve a little bit of visualization. In our next video, we'll talk about the vector nature of torque a little bit more, and have a little more rigorous mathematical treatment of what torque is, which we'll need for other purposes later on.